right, we're going to start. Let me double check that you all can see. All right, you can see. All right, so worksheet 25, particulate nature of matter. Right, now we'll jump into the first question. Now, some of you actually got this wrong. Now, this is a concept question. It's a very simple question, so you cannot afford to get this wrong. So if I've gotten it wrong, please make sure you pay more attention. All right, so you are heating from a solid to a gas. Okay, so which one decreases? So look at the word, is decreases. All right, so over here, the speed of particles from solid to gas, right? Actually, the speed will go faster and faster, right? So the speed will actually go up. So let me maybe just write here, solid going to liquid, and then finally to gas. All right. So if you're talking about going to the right-hand side, what happens is the speed, okay, of particles will go up. Okay, so that means particles move faster. Okay, increases. All right, then what happens to the distance? Okay, so the distance between the particles will also go, it will get wider and wider apart, right? So also increases. All right, so that's why A and B is not the answer. So you can actually tell from here, if I change to a highlighter, so this is solid, just look at the solid, this is liquid, this is gas. All right, so you can notice that the particles in the gas, they are far apart. Okay, particles in the solid, they are very, very closely put together. All right, so from solid to liquid to gas, the particles get further and further away from each other. Like, as if they don't like each other, they want to move away from each other. All right, so then how about temperature? Okay, now ask yourself, to change from solid to liquid, solid must gain heat or lose heat. Can you type into the chat? From solid to liquid to gas, all right, must the particles gain heat or lose heat? Type into the chat, please. Solid to liquid to gas, gain heat or lose heat? Thank you, Lavon. The rest of you, it's okay to get the wrong answer. We are here to learn from each other. I need to know which part you don't understand. Okay, good job, Yijie. So solid to liquid to gas, the particles gain heat or lose heat? That's my question. Larissa, good. All right, so please remember that going to the right is gain heat. Okay, so just remember going to the right-hand side, that means solid change to liquid to gas is gain heat. All right, so if you're gaining heat, that means temperature go up. Okay, temperature go up, increases. I do an arrow up. So here the temperature decreases, that's wrong, because I'm looking for something that decreases. All right, therefore the answer is D. Now what does it mean to have a number of particles per unit volume? Okay, so I'm going to draw what is per unit volume. Let's say this square is 1 cm by 1 cm and by 1 cm. Let's say it's a cube. All right, so this cube, right, is 1 cm by 1 cm by 1 cm. So the volume of the cube is 1 times 1 times 1. It will be 1 cm cube. So, but let's say I draw in 2 dimensions. So in 2 dimensions, right, if you take a look here in solid, how many particles do I have in this cube? All right, how many particles do I have in this cube? If you go to count 1, 2, 3, 4, 5, so 5, 10, 15, 20, 25. I got 25 particles. But how about liquid? If you really count how many particles there are in 1 unit volume, imagine unit volume is 1 cm cube. In this small little cube, how many particles are inside? So I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I got 19 particles in a liquid. Just now in a solid, I got 25 particles inside this amount of space. All right, per unit volume, volume means space. So in this amount of space, I got 25 particles. But in this same amount of space, I got only 19 particles. Then let's go to gas. In the same amount of space, I only got 1, 2, 3, 4, 5. Only got 5 particles. So poor thing. All right, 5 particles only. So let me write down. That's why here the number of particles per unit volume means in the space. All right, in the same space, number of particles actually go down, getting less because here is 25. this is 25, this is 19, and this is only 5 particles. So it's getting less and less. All right, so I'm going to write it here. So I have 25 particles here in the solid state. And then in the liquid state, if you want to go and count, it's about 19 particles in the same amount of space. Then in the gas, I only have 5 particles. All right, in the same amount of space. Okay, in this volume means the space. Okay, volume means in the space, in the cube. All right, therefore, as you move from solid to liquid to gas, there are fewer and fewer particles in the same amount of space. Reason being, the particles are widely, they are far, far away from each other. So in the same amount of space, you have very few particles. So is everybody okay now for this question? All right. Now let me double check whether anyone is in the meeting room. No. Okay, so I should have 6. Yeah, that's 6 participants. Okay, no one is in the meeting room. All right, let's move on to, okay, is there anybody who doesn't understand the first question? I'm looking for something that decreases. So the answer is the last one, because number of particles per unit volume, that means for every 1 unit of volume, every 1 unit of the space, it is fewer and fewer number of particles, because the particles move further and further apart. All right, so let's move on to the second question. Okay, question 2. Now from primary school, you have actually learned that, all right, let me use a laser pointer. Metal expands when heated and contracts when cool. It's quite easy to remember C and C, right? Okay, so if you remember your ball and ring experiment in primary school, you know, when your teacher heats up the ball, then the ball cannot pass through the ring, because the ball actually becomes bigger when the teacher heats up the ball. All right, and then when the teacher puts the ball in cold water, then the ball becomes smaller. Contract means become smaller when it's cooled down. So which of the following is actually correct? All right, just a minute. Okay, so over here, let's look at A. Now, particles decrease in size. Now, this says particles becomes like slim down. Particles decrease, become smaller and smaller in size. That's A. If you look at D, particles increase in size. Now, A and D are nonsense. All right. So always remember, the size of the particles remains the same. Size of the particles never change. So the particles, if you say particles increase the size, you're saying the particles get fatter and fatter. And then if you say the particles decrease in size, means the particles slim down, get slimmer and slimmer. Now, remember, particle size stays the same. All right. So what is actually happening is, all right, if I were to draw it in the solid state, all right. So if I, let's say, heat up solid at first, the particles are closely packed. Okay, so this is the amount of space they take. When I heat it up, right, the particle size is the same. I try to draw the same circle. Okay, same size, same size, same size, and then same size, same size, same size. And then when I heat it up, I still have 6 particles. All right. Okay, and then when I heat it further, all right, so let's see what is the amount of space that is taken. This is the amount of space taken. And then this is the amount of space taken. And then this is the amount of space taken. Okay, let me draw better. All right, so you can say that, okay, so here I'm talking about solid. Here I'm talking about liquid. Solid heat up become liquid, liquid heat up become gas. Right, so let me maybe draw this a bit same size, otherwise you might think it should be the same size. So this is the correct concept, all right, that the space that is in between, so here there's very little space between the particles, but here the space between the particles is more. Even for gas is even much more. All right, so particles in the gas are far, far apart. Right, so the size of the particles remain the same. What is different is the space gets bigger and bigger. All right, so imagine last time before COVID, we all like stand next to each other. All right, then during COVID time, we want to stand like that, right? And we queue up very far away from each other wearing masks, right? So during COVID time, we don't want to stand so near to each other. We are scared of spreading viruses to each other. So this is like during COVID time. Before COVID time, you just stand next to each other, no problem. Nobody will complain, all right? So the size of the particles remains the same. Only the space between the particles becomes wider and wider. Therefore, please don't tell me particles decrease in size, that's wrong. Please don't tell me particles increase in size is wrong. All right, so it's either the particles become further apart or the particles are closer together. So which one is correct? When heated, right, they should get further apart. When it's cooled down, they should get closer together. So remember, you heat up, you're getting so hot, right? You don't want to stand so near to your friend when your friend is, is on a hot day. All right, you're feeling so hot. Your friend is also feeling so hot. You don't want to stand next to each other and touching each other's very sweaty skin. So when you're heating the substance up, the particles are further apart. So the answer is B. All right, any questions so far? So let me write down the answer for this question. So these two questions, some of you actually got it wrong. So I'm going to write it here. Size of particles, all right, is the same. Even when you heat it or cool it, right? Even when heated or when heated or cooled. So it doesn't matter you heat up the particles or you cool the particles, the size of the particles remain the same. So I'm going to highlight here. All right, size of particle is the same even when heating the substance or cooling the substance. Please remember that. All right, so the particles doesn't get fatter or slimmer. Any questions so far? All right, let's move on then. Question 3, this is bromine. Now, bromine start with Br. Let me teach you in set 3, especially if you're that all of you are going to take chemistry. Now, Br, think of the word reddish brown. All right, so you need to remember the color of bromine gas. All right, so it's reddish brown. So it's easy to remember because Br, bromine start with Br. B stands for brown, R stands for red. So it's reddish brown, a bit of red, a bit of brown. All right, so it's some websites say brown gas, but it's good to remember it as reddish brown gas. So here I have a reddish brown gas in the gas jar, and then okay, here this one reddish brown. Okay, R stands for reddish, then B stands for brown. So it's a reddish brown bromine gas here. Then at the bottom, air. The air is colorless, no color at all. Please don't tell me white, huh? It's not white. White is different from colorless. White is like milk color. Right, when you drink milk, it's white in color. When you drink water, it's colorless. Okay, so then after some time, what's going to happen to the particles of bromine and particles of air? So actually, most of you would know it's because of diffusion is C. Okay, so those of you who came in earlier, I have shown you the video. If you came in late, right, you watch this video on your own, you can click on the yellow YouTube. All right, it's an active link. All right, it shows you the bromine gas diffusion. So diffusion basically is a movement of particles from a place or region of higher concentration to a region of lower concentration. All right, so this is slightly different from the question just now. The question just now was a brown gas is on top. Then the one in the video is the reddish brown gas is below. Now it doesn't matter. All right, at the end of the day, you will have the reddish brown gas in both gas jars. Okay, so we choose C is because A is very weird. You see this part shouldn't have the gas one. All right, this is the bottom of the gas jar. All right, so the gas will not enter the bottom of the gas jar. Okay, right, let's move on to question 4. Which one could be substance P? So you can see that, okay, if I were to shade the amount of space, this is the amount of space taken up by substance P. This is the amount of space taken up by substance P after you force the piston down. Okay, now it means that, can y'all type into the chat, what does this picture mean? It means that substance P can be what? What is the word I should be using? Substance P can be what? Can y'all type in the chat? Can be what? One word. Thank you, Larissa. Let me see. Thank